Hello students. So we now have a nice formula for the Stirling numbers. And let's write it down one more time. It might remind you of another formula that we have. And what this is saying is that Sn plus 1k is going to be, well, these each get lowered by 1, and then I have k times Sn. Okay, this looks a lot like Pascal's formula. So for the Pascal triangle, for the binomial coefficients, we would have C n plus 1 k is equal to C n k minus 1 plus C, each one is lowered by 1, and then this. So n k. So this is our Pascal's formula, and this is our Stirling formula. So from Pascal's formula, we can make a nice pyramid, and that might make it easy for us to compute the binomial coefficients for low values. Maybe not for high values, but for reasonably low values, we can do it fairly fast. Now, what about for this one? Could I make a pyramid out of this? And the answer is yes, I could, but I just have to watch out for this multiplier. So let's think about how I could do that. Well, one thing I could do is I can put the Stirling numbers here. Let's do S21, S22, S23, S31, row 3, 31, 32, S33, and so on. So this would be S41, S42, S43. And I'm just going to do this the same way I would with Pascal, and these are going to be my n's. So this is n equals 1, n equals 2, n equals 3, and n equals 4. And these on the diagonals are going to be my k's. You could see each of these has a 2 in the k slot. K equals 2 on the diagonal. So the k's are all on these diagonals. And let's say I wanted to find one more. Let's say I wanted to find, let's see, which would go here. This would be S53 because we have all the diagonals there are 3. Okay, so let's try to think about this for a little bit. How would I get S53? Well, I would take the one with both of these numbers lowered by 1, which is here and which is up to the top left. And then I take the one where only the n is lowered by 1, which is over here. I'm going to add it, but I'm not just going to add it, I'm going to add a multiple of it. And what is that multiple? Well, it's whatever is here. So in order to get this, I'm going to take this plus 3 times this. This plus 3 times this. And that's true for anything. If I wanted to find S54, I'm going to take this plus 4 times this. This plus 4 times this. So I could use this to pretty effectively come up with a pyramid. Now, I know that if I have n objects, no matter what those n objects are, and I want to group them into one set, well, there's only one way to do it, and that's to put them all together. And I know if I want to group them into n sets, there's only one way to do that, and that's to keep them all apart. So what does that mean? Well, it means the numbers on this diagonal here, which are the number of ways I can split things into one set, well, those are all going to be 1, just like with Pascal. And here, this is the number of ways I can split n things into n sets. That's also going to give me all 1s. So just like with Pascal's triangle, I'm going to have 1s down both diagonals. Okay, so now let's try and make a pyramid using this. So 1, 1, 1, 1. Oh, let's do this step by step. Okay, so this is n equals 1, so we don't make that mistake or a mistake. N equals 2, n equals 3, and so on. And now this is going to be k equals 1, and this is going to be k equals 2. Okay. And as we keep going, this is going to be the k equals 3 on these diagonals. Okay, so to get this number, I don't put a 2 there. With Pascal I would. What I'm going to put here is going to be a 1 plus 2 times 1. 1 plus 2 times 1, that gives me a 3. Okay, so now for the fourth, I'm going to put a 1 and a 1 there. Now for this value, this is n equals 4 row. Okay, I'm going to get 1 plus 2 times 3. So that's 1 plus 6, which is 7. And for this, I'm going to get 3 plus 1 times 3. So that's 6, because that's 3 plus 3. K equals 4. Okay, so now for the n equals 5 row. I'm going to get 1 plus 2 times 7, so that's going to be 15. And then I'm going to get 7 plus 3 times 6. 7 plus 18 gives me 25. And now I'm going to get 6 plus 4 times 1, well, that's just 10. And I can keep going like this, and you'll see this is going to be each of the Stirling numbers. Do maybe one more, since this is not so bad. 1 plus 30, that's going to give me 31. And now 25 times 3 is 75, and 15, that's 90. 4 times 10 is 40, that's easy. 40 and 25, that's going to give me 65. And now I'm going to get, this is k equals 5. I'm going to get 10 plus 1 times 5, which is 15. So what this is telling me, for instance, is the number of ways I can place 6 objects in 5 sets. There's 15 of them. And we can actually just confirm that. If I have 6 objects and I want to place these in 5 sets, what does that mean? Well, it means that 2 have to be in one set and all the others have to be alone. So basically, all I have to do is think about the number of ways I can choose 2 to be in the same set, and the others all get their own. I have 6 elements, it's going to be 6 choose 2. And that's 15. So that confirms this value here. Of course, normally, you don't just get a binomial coefficient for your Stirling numbers. This was over here on the very edge, which is what allowed that to happen right there. But okay, so now what did we do? Well, we were able to use Stirling's formula, which is a lot like Pascal's formula, in order to get our own triangle for the Stirling numbers. And when I'm just saying Stirling numbers because so far we only have Stirling numbers of the second kind, so it's just easier to say, hey, these are our Stirling numbers. So we have a Stirling recursion and a Stirling pyramid, which can be used for computing these for low values fairly quickly.